Hi, and welcome to the first lesson for this course. This course is a sequel to the first calculus course in the Mastering Mathematics for Engineering program. In that first course, you learn all about functions, or at least about single variable functions. Indeed, a function was defined there as a gadget which associates a real number in the range to each real number in the domain. When modeling complex situations, we will see that quantities often depend on more than one input variable. For instance, the temperature on Earth varies not only with latitude, but also with longitude. And so temperature is a function of two variables in that sense. Similarly, we know that a gas expands when temperature increases, so that its volume is a function of temperature. However, we can decrease the volume by putting it under pressure, so that volume is also a function of pressure. In fact, the ideal gas law indicates that the volume of an ideal gas is a function of both temperature and pressure. These are still rather mild examples of the main topic of this course. This topic is again functions, but this time functions of several variables. Here is the definition of a function of several variables. Again, it is a gadget that associates a real number to a point in the domain, but now it takes as input not just one real number x, but a bunch of real numbers x1, x2, etc. up to xn. Note that if n is equal to 1, this reduces to the case we saw in the previous calculus course. And indeed, what we consider here is a generalization. This means that we'll have a look at a lot of analogs of concepts that we already saw for functions of several variables. In particular, visualization, differentiation, and integration. For this first lesson, we will restrict ourselves to the concepts of a formula, domain and range of a function of several variables, together with some examples. First of all, recall that the best way to define a function is by way of a formula. This gives a set of arithmetic operations that you should perform on a variable in order to obtain the function value associated to it. On the slide, you can see an example for the case of a single variable function. This notion generalizes quickly to the functions of several variables. Again, a formula simply tells you what arithmetic operations to perform with a bunch of variables together to obtain the function value associated to that bunch of variables. On the slide, we see again an example. In the definition of a function of several variables, we saw that we only consider those combinations of input variables that are included in the domain. In general, the domain is a part of the definition of the function, so it can be determined nearly as you please. For example, we may consider the function f, which associates to any pair of numbers a and b, where a is strictly between 0 and 1 and b is strictly between 1 and 2, the number a times b. In that case, the function value at the point 0.5, 1.5 is 0.75, while the function value at the point -10, -11 is simply not defined, since it is not in the domain. In fact, even the function value at the point 0, 1 is undefined, since the inequalities describing the domain are strict. If you would press us to come up with a function value at that point anyway, we would probably say 0, since 0 times 1 equals 0. In fact, if you would press us about the first point, we would probably say 110, since -10 times -11 is 110. What we are intuitively doing here is considering the so-called maximum domain. The maximum domain of a formula consists of all the points where the formula makes sense. This means that we need to refrain from things like dividing by 0, considering the logarithm of non-positive numbers, and considering the square root of negative numbers. For instance, the maximal domain of the previous example formula is simply all pairs of real numbers. If we ever provide a function without explicitly mentioning the domain, but we do mention a formula, you may assume the maximal domain. Here is another example of a function of 4 variables given by a formula. Take a moment to read the formula, and then note that the maximal domain indeed simply consists of those points such that we do not divide by 0, we do not have negative numbers in the square root, and we do not have non-positive numbers in the logarithm. Considering again the ideal gas law function we saw earlier, we find that the maximal domain is given by all pairs of numbers t and p, where p is non-zero. In other words, we could consider the plane with the vertical p-axis removed. Of course, this is a bit strange, because t and p are not numbers. Actually, T is the temperature, say in kelvins, and P is the pressure, say in Pascal. Taking that into account, it makes sense to reduce the domain and consider only those points T, P, where T is greater than or equal to 0, and P is strictly greater than 0. So what we have here is an example of the common situation where the domain we actually consider in practice is not the maximal domain, but rather a smaller domain. Indeed, given a formula for a function, the domain of that function must be some part or the entire maximal domain. On the other side of the domain, we can also consider the range. The range of a function consists of all real numbers that occur as function values for points in the domain of the function. Sometimes we will be particularly interested in the highest or lowest values in the range. These are called extreme values and are the particular topic of the 4th week of this course. In the coming weeks, we will generalize a lot of concepts we know from functions of a single variable and show you how to work with functions of several variables, as you are used to do with functions of a single variable. Before we get started on that, however, make sure to have a look at the exercises following this video.